It is my pleasure to introduce our next speaker, Dr. Joel Andersen. Joel received his bachelor's degree in chemistry from St. John's University in Minnesota. He also has a master's degree in environmental sciences and a Ph.D. in organic chemistry, both from the University of Cincinnati. During his Ph.D. work, under the supervision of Professor James Mack, Joel's focus was on identifying, isolating, and controlling the principal factors that determine the energetics of mechanochemical reactors. Joel is now the Chief Technical Officer at Cinthesis, a University of Cincinnati spin-off startup, whose goal is to help introduce mechanochemistry to their repertoire to achieve reactions in a cheaper, faster, safer, and a more environmentally friendly manner. Welcome, Joe, and the floor is yours.
Okay, thank you for that introduction. So my goal with this presentation, since I think I might have kind of a wide audience, is to really bring along as many people as I can from the first slide up to the last slide, since this is both organic synthesis and extrusion all in one. Hopefully I'll be able to keep that audience listening in the whole time. So organic synthesis, there's a lot of small scale research and development that gets done. And then with successful drugs or other products, it has to be scaled up for manufacturing purposes. And so if somebody's like myself is going to work on developing new methods, we need to be able to do them on both the small scale and the large scale. And that's really where the reactive extrusion comes in, is for the large scale part. So just to add a tiny bit to the introduction, Cinthesis is a combination of Cincinnati from Cincinnati, Ohio, and Cinthesis, as in organic synthesis. Well, as was mentioned earlier, really our goal is to help industry include mechanochemistry and solvent-free synthesis into their toolbox, which is what chemistry is all about, at least for synthetic purposes, is adding to our tools for making new ways to make chemical bonds. And so there's a lot of hocus pocus that's associated with mechanochemistry, and part of what I do is to hopefully remove some of that hocus pocus and not make it seem too mystical or magical. And then the last part is understanding the mill to the extrusion translation. So how do we get from these milligram scale reactions up to the larger scale reactions in the extruded? So there's three of us right now, myself, and then I also work with my former faculty advisor, and we're also working with Ed Sawicki, who worked for Procter & Gamble. He's kind of our business expert on the matter. So when it comes to the process of actually performing a solvent-free reaction, it helps to kind of compare it to what everybody, as far as chemists, are going to be used to when it comes to doing reactions. So if you've got reactant A and reactant B, you'll throw them together on a small scale, which would be into a round bottom flask, add some solvent, heat and stir, and then you'll end up with a product given the right amount of time. In the mill, it's not too different. So the mill is the box that you can see down here. So this is kind of like a paint shaker, and into that mill, we place a jar that contains our reactants A and B, and then also a stainless steel ball. You could also make the ball and the jar out of Teflon or any other types of materials, but in this example, this is a stainless steel jar. So once you place it in the mill is going to be shaking back and forth like a paint mixer, and then that'll force the stainless steel ball to impact your reactants, and then that'll decrease their particle size and eventually allow them to react together. And nowadays, it's a very simple matter to just heat it at whatever target temperature you want to set, allow it to continue grinding, and you end up with a product in a similar manner. And again, this is kind of the small scale mechanochemistry. So when might you want to do mechanochemistry? Well, certainly it's not limited to these types of situations, but these are just some times when you might want to consider mechanochemistry. Let's say your materials are very poorly soluble, well then you're going to suffer from poor kinetics and an undesirable process mass intensity. So your reaction might go really slow because the solubility characteristics mandate that you have to be fairly dilute, and then since your concentrations are low, your kinetics are going to be low. If you're not dissolving anything like in a solvent-free system, then you don't have to worry about solubility. So you completely skip over that, the dilution penalties that are coming from situations of high dilution. Or maybe you're stuck using an undesirable solvent like DMF, or you have to use an anhydrous solvent. Since a lot of the times a solvent could be kind of a Trojan horse when it comes to water. If you don't have a solvent, you're not going to have any opportunity for water to come in except for through the atmosphere in the headspace of the reaction. But it's very simple to remove that or to replace that atmosphere with an inert gas, and so that allows you to completely bypass any of the issues regarding mandating dry solvents. And so harsh conditions could come along, especially if you are stuck with high dilution. Maybe you have to heat your system up pretty hot in order to overcome those low concentrations. In our situation in mechanochemical systems, you might think of it like you're kind of at the max concentration you can possibly be at. And as it turns out, that often saves about 40 to 60 degrees Celsius, which can have significant impacts on things like selectivities of systems, which offers up yet another entire reason to do these reactions solvent-free. Similarly, if your reactants have very different solubility characteristics, you might have to do a biphasic reaction, and then you've got, you might have issues separating out your phase transfer catalysts that would be needed. And so there are a number of reasons for doing reactions mechaноchemically, and it's not limited to this list here, but these are just some food for thought. So this is a list here of transformations that can be done through mechanochemistry. So to a non-organic chemist, this might not have a whole lot of meaning, but it's just to demonstrate the breadth of what can be done mechanochemically. If a reaction transformation that you're interested in is not on this list, it's not because it can't be done mechanochemically, it just maybe hasn't been done yet, or I didn't happen to stumble upon it when I was making this list. So this list is really over the last 15 to 20 years or so of mechanochemistry. And, like I said, it's by no means is it, if your reaction's not on here, don't think it's not because it's not possible. This is just what has been done so far. So mechanochemistry, there's opportunities for it, and it's actually, this is to demonstrate that it's capable of doing quite a broad array of reactions as well. Mechanochemistry is very useful. It'll also be capable of achieving probably just about any transformation you might be interested in trying to do. So the last component that I think is necessary to understand is about the reactors, especially the small scale reactors. This presentation is going to be talking significantly about the scale-up side in the extruder, but you also want to make sure you've got a good idea and a good understanding of the reactor on the small scale. Because if you're transitioning from one reactor to another type, you're really going to want to understand how the reaction's proceeding and what kind of factors are influencing your reaction. So before 2015, kind of the idea in mechanochemical systems was that the energy for a reaction was coming from the kinetic energy of the ball, which is kind of what this figure on the right side is supposed to show here. That ball is impacting the jar wall, and then there's a direct conversion of kinetic energy into chemical energy. At least that was the belief at the time, and over the last 5 or 6 years, this has really kind of been set aside in favor of the understanding that what's really important, especially if you have just a single ball, is just the bulk temperature of the vial. So if you have, a lot of balls inside the jar, they're going to produce their own heat, and then you've got separate issues there. But if you have just a single ball and you can control the bulk temperature of the vial, then that's the most important part. And that's, just back in line with normal chemistry as far as somebody's concerned. Temperature is a very important thing to control in your reaction, and it's the same way for a mechanochemical system. Frequency describes how fast the machine is moving back and forth. And so when it's shaking, you can make it go faster or slower, and that can have some input. Certainly, if the machine isn't moving at all, then you're going to have mass transfer limitations. But beyond a certain frequency, mixing faster doesn't necessarily provide a faster reaction. And the vial and the ball hardness can have an effect as well. Really, those bottom two are more about mixing, and the top one is more about activation energies. So these were two examples from my thesis that I'll just give real quick. Again, this is on the small scale, about 100 milligram scale reaction. As you go from the left to the right, you've got 3 different reactions happening, and each one basically turns from 0% conversion all the way up to 100% conversion within about 15 or 20 degrees of temperature. So for the last reaction, if your reaction vessel is not above 80 degrees, that red line stays at 0. But as soon as you're at 100 degrees Celsius, you get to 100% conversion. So it's really important to be able to control temperature. And for anybody who's familiar with extrusion, controlling temperature is actually, quite a simple thing, at least in comparison to some of these small-scale mechanochemical reactors, although it's becoming easier and easier as the technology is catching up to the science. Similarly, we can also do cold reactions. So it's useful to be able to do high temperature reactions, but going below 0 Celsius is actually ideal, and it's not included on this figure, but we've done reactions as low as -10 Celsius. So now getting into the present work and the reactions that we scaled up, we did 2 different reactions. We looked at nucleophilic aromatic substitution reactions, which is abbreviated as SNAR. We picked SNARs for 2 reasons. One is that they are extremely common. So if you look at the left, you can see in 2014, it was the 2nd most common in the Journal of Medicinal Chemistry. So it's extremely common, but unfortunately, it often requires a solvent like DMF. And so these solvents are in the hazardous category. And, for the actual reaction itself, it'll benefit a lot from using DMF. But what we've seen, and as you'll see shortly here, is that we can completely remove DMF. And then in the workup part where we purify our product, at that point, we might be able to use something like water and ethyl acetate. So sometimes people will say in mechanochemistry, you still need to do a workup, and that might include solvents, and that's true. But in this case, we're removing, a very undesirable solvent like DMF. And for the workup, we've got a little bit more freedom, and we can stick to these recommended solvents. I've got an example of a transformation that happens with an SNAR. So this chlorine here is going to be our leaving group, and our nucleophile will come in, displace it, and we've made a new carbon-nitrogen bond. And so, this type of transformation is very common in medicinal chemistry. And so that's, these reasons together are some of the reasons that we chose the SNAR reaction. And I'll get into more about the Canova-Nagel reaction and how we ended up choosing that one. So this is the groundwork that we did when it came to understanding the SNAR reactions, because before you can scale something up, you really need to understand it on the small scale, especially when it comes to temperature. So in this case, I've pointed out that our SNAR work here is isothermal. Normally, a chemist might not even specify something like that because it's just understood. If you say your reaction's done at 60 Celsius, it was done at 60 Celsius, the entire 10 hours that the reaction proceeded. But, historically in a mill before the technology existed, a reactor's temperature was not necessarily even really known, and it was actually changing throughout the course of the reaction as the reactor was heating up. But in this case, now we've got the technology where we can just choose whatever temperature we want, and then we'll be doing our reaction at that temperature for the duration of the reaction. So now, at this point, you've got one-to-one comparisons. The conventional manner of doing this in DMF, for example, up here is in purple, and we've got our comparison in orange triangles for mechanochemistry. So each of these examples has a different set of reactants, and they were performed at different temperatures. But in each of the cases, you can compare mechanochemistry versus DMF and see how it performs. And as you know, these figures and the table on the right make clear, in all cases, mechanochemistry performed the reaction faster, and it also ended up getting higher yields in every single case. On average, you can see that it was about 9 times faster to reach 95% conversion. And again, this is just on the small scale, but what we're seeing here is that once you control temperature, our curves are very normally shaped. So it's not like there's any kind of magic going on here in the absence of solvent. You know, these are reliable, predictable, well-defined curves that are not too different than what people are used to with DMF or, you know, just a conventional system in general. And so now that we've got a well-understood system, we can consider something like scaling it up. So on the left is our milligram, maybe up to a gram batch operation in a mill. And then on the right, you've got an extruder. So you've got a hopper up here, you put in your materials, it'll travel down a barrel that can be temperature controlled and then come out the end. And then that could get, depending upon the system, you know, tens of grams or kilograms per hour, and it's a continuous operation. So materials are continually fed in and are continually leaving. Now, we also have to think about how the mixing forces are changing when we move from one system to the other, because we can control temperature, but we also have to think about how the mixing might be changing. When you have just a single ball, you've got a lot of compressive type forces in the mill, but when in the extruder, you've got these two screws that are inside the barrel, and as material is being moved down those screws and grinded between them, you not only have compressive forces, but you've also got a significant component of shear. And so that'll be something we want to think about when we're looking at any results and trying to understand them a little bit better. And then the last component is really to know that a residence time, which describes how long your reaction or your reactants are in the barrel, which is the reactive part of the extruder, how long it takes to enter, or how much time passes between the moment that they enter and the moment that they leave. And that's going to be, again, chemists are targeting high residence times because typically our reactions take a little bit longer than a normal extrusion process, which might be only 30 seconds or 1 minute or 2 minutes. But a reaction, you know, going 24 hours is not unheard of. But what we found is that we can get about 5 to 15 minute residence times, which means that our reaction times in the small scale need to be 5 to 15 minutes. And so one thing we need to think about that, or consider when we're thinking about that, is if we heat up a jar, it starts at room temperature, and let's say we're trying to get to 100 degrees, it takes a little bit of time to get there. But if you preheat the jar, then you are much closer to your target temperature for a much larger percentage of that time. You know, just as an example, if your reaction time was 10 minutes here, almost half of it you're spending below 70 degrees. So one thing we did going forward was to preheat the jar and make sure that it was as close as possible to its reaction temperature from the get-go to minimize the amount of time that it took to heat up a small-scale reaction. So here's one of our SNARs that we did. Notice in the previous example, chlorine was your leaving group. Fluorine is actually more common for SNAR reactions, but with fluorine is our leaving group, and we formed a new carbon-nitrogen bond. And in this case, we've got various temperatures that we did this reaction at, and each reaction was done for 15 minutes. You can see a general trend going up. It's actually not too temperature sensitive. You know, this is a pretty broad temperature range. So this is one of the less temperature sensitive reactions I've seen. And it actually seems to stall out for a little bit here. And what we really decided is that this is probably a result of, since you have no solvent, uh, the, the mixing characteristics of this product as it accumulates, reaching about 90% conversion, maybe this product is a little bit tougher to mix. And so it takes, it slows down the reaction as this product becomes a little bit more difficult to mix. And then eventually you get the temperatures high enough that it overcomes those mixing challenges. But this gave us enough information to say, okay, well, when we put it into the extruder, we can expect full conversion at some point between 40 degrees and 110 degrees. And so we don't even have to think about something like 200 degrees or 300 degrees when we're approaching the extruder. So what we do is, in the case of the extruder, we pre-mix two of our solids that wouldn't react with each other, fed them in at a known rate through the hopper, and then at a separate point through a syringe pump, we injected benzylamine, and we put them in at known rates so that they would stay in only slight excesses relative to one another. And we got really quite a nice curve. So in this figure, you've got temperature of the barrel in red here, and that axis is on the right. And then you've got the conversion on the left axis, and so that's your circles. So as we take these stepwise increases in temperature, we can see stepwise increases in yield as well. And at each temperature, we get fairly reproducible yields or conversions until we change and increase the temperature. And as you can see here, it actually looks like we don't bump into the same issue with conversion. And if we want to take a look at that, this is the same data on the left here. On the right now, you've got this extruder data. Each data point was averaged together. So for example, here you're starting off at 40 degrees. If you average these three data points together, you get this. So on the right, you've got kind of a bar graph if you want to compare the extruder to the mill. And it's not perfect, it doesn't go one-to-one, but the agreement is definitely there. And I think, this kind of approach of getting as much information as you can on the small scale to inform the scale-up process, you don't want to ignore the temperature the temperatures that you find on the small scale, because it's very useful for scaling up. And definitely, once again, you can see here that it doesn't bump into the same leveling out effect. And so we kind of attributed this to the shear that comes along with performing reactions in the extruder. And one thing that we thought is maybe if we introduce another ball when we do it on the small scale, that we won't bump into that issue. And this is where things really got interesting. When we did two balls, we ended up getting really nice agreement between the extruder and the milling experiment. So the thought process here is that with the inclusion of an additional ball, you end up incorporating a little bit more of a shear force in there. And in this example, that becomes extra helpful, especially as you approach those upper conversions. And so, it's not necessary to have perfect agreement between the two of these because they're not the same type of process. One's a continuous process, one's a batch process. But it's still very helpful to have knowledge regarding temperature effects on the small scale as you're heading into the scale-up process. Because once you get above that milligram scale, you really don't want to have to invest too much money material-wise in order to reach your final process parameters. So we also looked at Canova-Nagel reactions, and so here you can see this was also done in the mill initially. Here you get much stronger temperature dependence. So as you go from 30 to 40 to 45, 50 to 60, you go basically from almost 0% conversion on up to 100%, much smaller range. We initially tried to do this in the mill, in the extruder, now that we saw we can get up to 100% conversion, and it gives us our anticipated extrusion temperature ranges. But we ran into an issue with torque overages and also heating of the barrel above the target temperature. So in this case, the materials that we were including were tough enough to grind, since they are not in fact melted. They're tough enough to grind that it starts giving off excess heat above the target temperature. So if we set the barrel to be 35 Celsius, in this first entry, you can see that it actually reached almost 50 degrees because of the excess heat that was being given off. And so I don't really have time to get into each of these mixing configurations. We'll be publishing this in collaboration with Thermo Fisher pretty shortly, hopefully. So there's more information on this, but as you proceed down a screw, you can have various mixing sections that each have different mixing characteristics, from very high mixing intensity to low mixing intensity. And if you go through that paper, you'll be able to read a little bit more about this, but we ended up going with this configuration ID number 3 because it gave us the ability to target the temperature that we wanted pretty closely. We were looking for 35 and we could get about 36 or 37. And we still got a reasonable residence time around 5 or 6 minutes. So with this configuration, we no longer had those issues with temperature overages or torque overages. And we moved forward with the extrusion and looking at conversion. So at this point now, we've got another of our figures where we're comparing milling conversion to extruder conversion at the same temperature, or at least, within a couple degrees of each other. And so the previous data from the milling conversion is no different than you saw before. The only difference is that now I've got the extruder data included here as well. And again, you can see very good agreement between these two. It's not perfect, nor should it be, because these processes aren't one-to-one. But it's still very helpful in identifying what temperatures can we expect to require from the extruder, and that can really limit the amount of guesswork that's required once you're scaling up into the extruder. And going forward, we plan to look at other examples of reactions and continue to add to the body of work that kind of helps everybody understand this process of converting from milligram scale R&D data up into the upwards of kilogram per hour potentially applications of extruders. And so I hope people have kind of seen that twin screw extrusion can certainly work for scaling up solvent-free reactions, and it can actually be really well informed during that scale-up process by the information that's learned on the small scale. A lot of small-scale mechanochemical reactors are not by default going to have the ability to control temperature, but if you go back in this presentation, there's some citations, and it's revealed in those documents how to modify your mill so that you can control temperature and develop that kind of knowledge that really helps for the scale-up process. So if you're interested in learning more about mechanochemistry, we would be happy to talk with anybody out there who wants to learn a little bit more about it, and especially incorporate it, whether it's on the small scale or the large scale or both. Or if you just happen to have any quick questions about mechanochemistry, you can certainly drop me a line, and I'd be happy to talk with anybody about that. Thank you.